Hey everybody. Welcome to week 2 of ARM 2. This week we're going to be doing or talking about bivariate correlations and bivariate regression analysis. The text for this week is it's a little dense, but I think the chapter for this week has an awful lot of math in it, mathematical proofs. I'm gonna try to boil down a lot of this to make it a bit more understandable, um, and we're gonna do a lot of stuff in class this week. So I'll talk a little bit more about that as we get going. But let's start by representations of data. We're going to have a few of these. We talk about these are 4 different representations of basic correlational data. This is bivariate data, the relationship between X and Y, or A and B, whatever you want to call them. You should all know at this point that correlation coefficients range from -1 to +1, with the strongest relationship being the absolute value of 1. 0 being no relationship at all. So if we look at these graphs, we see that, or these figures, I'm sorry, we see that in figure A, we have basically a perfect relationship. You see that there are a number of observations, and that those observations fit perfectly on a fitted regression line. This would be indicative. I think a lot of people believe that a correlation of 1 actually means that there is the magnitude of the line means something, but that's not necessarily the case. It's not an issue of the magnitude of the line. It is an issue of the magnitude of the residuals, or the squared residuals. And residual, you'll hear me use this term interchangeably, residual and error, throughout the day today, or throughout the day tomorrow. But residuals are the distance that a given observation is from its expected value. And that is the spot on the line where it should fall. So for example, right here, we would predict y, this assuming that this is a value of y, right? Or this is a value, and we have y right here, and we have x right here. And we would predict that this value actually would be right here. And the fact that it's not, this little bit of area is called its residual. We have residuals above the line, and we have residuals below the line. And these residuals add up to 0, which is why we will wind up squaring them. We'll talk about that as we get going. But back to this, we have a perfect correlation, a correlation of 1, where there is no residual. Everything fits perfectly. In truth, we're not going to walk through the math of this, but this is actually a value of 4, and correlations can technically go from a value of, squared correlations can go from a value of 0 to 4. But we're not going to worry about that. Right now, all you need to worry about is true correlations, and bivariate correlations technically go from -1 to 1. This is another very strong positive correlation. So in A, we have a perfect positive correlation. In B, this would be actually a weak negative correlation. That's actually a modest negative correlation. I wouldn't say it's necessarily weak. Something to note that we're not going to talk about this week, but that we will start talking about in 2 weeks, are observations like this. This little dude down here is likely an outlier. You can see it's got a huge residual. That's something that we will be discussing later on. Here is another very, very strong positive relationship, and then we have a positive relationship here. This is more often what our data look like. So anyway, this is how we represent them. It's always good when you're doing bivariate correlations just to have a look at these. It's also sometimes nice, and we'll talk about this as we get going, to look at the distribution of the actual residuals, because one of our assumptions has to do with the distribution of those residuals. So we can have a positive linear relationship for a correlation. We can have a negative linear relationship for a correlation. We can have no relationship, right? The fitted line would go right through here with the residuals above that line and the residuals below that line canceling each other out. The way that we fit that line is by fitting a line of residuals equal to 0. This is a curvilinear line. If you try to fit a straight line through here, you're to zero out those residuals. You have positive residuals and negative residuals. That's positive predicted values, negative predicted values. The straight line would be a correlation of 0, but in truth we can fit a curvilinear line, at least in the regression portion of this, to have a curvilinear effect. It's called an X, well, we'll get to that. And the same thing here. We have a curvilinear effect here that should be a correlation of 0. We'll talk about curvilinear effects 3 or 4 weeks, I think. All right, so let's talk a little about the index of the linear correlation, or the most common type of correlation that we use today, which is the Pearson product moment correlation coefficient. And the reason that we call it a product is because it is actually a product. Recall that a product is the multiplication of two variables. So in the Pearson product moment correlation, what we are doing is we are essentially looking at the relationship between two, at least in the case of a correlation coefficient, between two standardized scores. Now, when you talk about two variables, the relationship between two variables are represented by an overlap in a standardized level of variance, or a standard deviation from their mean. But oftentimes these are not measured on the same unit, right? So for example, we might have the relationship between age and weight. Age is obviously measured in years or months or seconds. Weight is measured in pounds or kilograms or tons. They're not measured in the same unit, and so understanding the relationship between two variables based on different units can be difficult. We use a standard score system in order to do this that converts variables to standard units with a mean of 0 and a standard deviation of 1. This is essentially a z-score. And this z-scores, or this standard scoring system, has 3 basic components. First, the sum of a set of z-scores, and thus the mean, are equal to 0. By the way, we're going to do this in class, so don't worry too much about it, but we're going to calculate z-scores from data. We're going to convert our data into actual z-scores, and then we're going to do some interesting stuff. The variance of a set of z-scores is equal to 1. Remember that variance is just the standard deviation squared, and so if that is equal to 1, then the standard deviation is the square root of the variance, also is going to be equal to 1. Neither the shape of the distribution of x nor its absolute correlation with any other variables is affected by transforming it to z, or any other linear transformation. We'll talk about linear transformations that we can do. We also will wind up doing some nonlinear transformations to address issues associated with assumptions. Right now, we're not going to worry about that. Just know that a simple linear transformation, which means adding or subtracting a value from your distribution, or from your values of x, have no effect on the absolute correlation with other values. And the Pearson product moment correlation coefficient is actually the product of two z-scores. So it's z of r, or zx times zy, and then you add all of those up, and then you divide that value by n minus 1. We're going to do this in class. This is an interesting exercise to calculate or show how to calculate the correlation between two variables. So we're going to focus primarily on the Pearson product moment correlation coefficient, which is ideally used when you have two continuous variables. If you have one continuous variable and one dichotomous variable, you can use the point by serial correlation coefficient. In addition, a continuous variable with a dichotomous variable, if you do not want to do a correlation, we'll do this in class also, but the correlation between the two and a t-test or ANOVA using the dichotomous variable will produce the exact same result. We also have phi coefficient. This is when both of the variables are dichotomous. This allows you to look at correlations when you have a bunch of ones and a bunch of zeros. An alternative way of thinking about phi coefficient is another way to represent a basic chi-square. And then we have rank. When we have two sets of ranks, if you have just one set of rank, so for example, if you were to correlate a person's place that they finished in the race and their time, that is one rank and then one time variable. You could use a actually, that winds up being two ranks, doesn't it? In that case, then using a rank order correlation would work. There are times when using rank might not involve two ranks, in which case you could use, so for example, if you wanted to correlate the order that people came in at in a marathon and their body weight, you could use a simple Pearson product moment correlation coefficient. You don't need to use rank order correlation coefficient in that instance. So, all right, let's talk about regression coefficients. Just by way of mentioning this, regression coefficients come in two basic flavors, at least linear regression coefficients. You have an unstandard regression coefficient, which is usually indicated using the letter B. We also have a standard regression coefficient, and that is usually indicated using the Greek letter beta. The nice thing about standardized coefficients is they are a direct comparable measure of effect. And in fact, a standardized correlation coefficient is the actually in a bivariate regression analysis the same thing as a simple bivariate correlation. What you're going to find in this class is a lot of times the regression, the statistics that you've heard about are fairly interchangeable. So correlation and regression, correlation is really just a special case of bivariate regression. So anyway, we will go through that too in class today. We'll talk, or tomorrow we'll talk a little bit about that, or this week, class this week. Bivariate correlation assumes each variable is asymmetric. That means that they are of equal importance in some fashion. That's not always the case though. In fact, most of the time in research, we're trying to understand the variance in Y, and we're trying to use things to predict the variance in Y so that we can understand them. In fact, this is the whole point behind inferential statistics and regression analysis. If you think about it, if everybody were exactly 6 feet tall, then we would have no need for statistics. There would be no variance, we would all be 6 feet tall, and there would be no need to try and explain why somebody wasn't 6 feet tall. However, if the average is that people are 6 feet tall, and that some people are taller and some people are shorter, then we have variability away from that mean. We have deviations away from both above and below that average of 6. And our goal then, assuming that the true average is 6, our goal then is to understand what things predict whether or not you are not average. And that's the basic idea behind regression. You have an intercept, that is the average, and then you have some sort of a value right here that explains the magnitude of deviation from that average as a function of this, as a function of x. X explains why you are 1.3 away from this, or something along those lines, right? So we assume that there's a predictor and an outcome, and that they have both scientific and technical importance. We're not going to worry too much about the technical importance. We're not going to be doing proofs, mathematical proofs. If you want, you can work the proof out in Chapter 2 for correlation. We will do a rough proof in class for a correlation coefficient, just to kind of give you an idea of what I think it's important to at least do that. But we're not going to work it out by hand. We will do it in Excel, and it will only take us a few minutes, but we'll do it. And that will also be part of your homework this week. So we're going to focus more on the scientific importance, and that is understanding what this algebraic equation really means. So let's look at these for a second. Y hat, this is called y hat of I. So this is for individual I, the predicted value. This is the value of y on the line, where it should be. Not where it is, but where it should be. The estimate of the regression intercept. This is the average, right, or the spot where the line touches y. And that, where that line, where this equation starts on y, is the average level of y. It's the average predicted level of y, right? It's not the true level of y. And everything is relative to the predicted level of y. Then we have x, and this is any value for x for person I. So if person I is 4, then we have the slope. And this slope says that this value times this value should give us the predicted value of y plus this value. So if this is 0.4, then we would have 0.4 times 4, assuming that this person's x value is 4. That means that, and let's just call this 0 for right now. If this were 0.4 and this were 4, then we would have 1.6 as a value of y hat. That means that when x is 4, this person's value should be 1.6. It doesn't mean it will be, because we have something missing from this equation. Sorry about that, which is our error or our residual. So technically, but it's not missing from this equation because we're predicting y hat. If we removed this hat, then we would have y equals b0, our intercept, plus b1, our slope, times our person i's value of x, plus residual. That accounts for the difference between y and y hat. All right. So taking just a break real quick, since we're starting on regression, let's talk a little bit about regression toward the mean. We all have heard about regression toward the mean. I think there's a layman's belief that regression toward the mean is an artifact of regression that is simply due to the analytic procedures that we use in regression. That is not true. Regression towards the mean is a mathematical necessity that's linked to the idea that extreme scores on one variable will necessarily result in less extreme scores on its counterpart. And in fact, extreme scores produce high residuals, and across time, residuals tend to move away from that, away from extremity. That is the very kind of nature of regression. Regression is seeking to minimize residuals. And so at any given time point, at any given sample, you may have some extremes, but in general, those extremes work their way back across samples or across time. So, for example, extremely overweight people tend to lose weight across time, or people who are not quite as bright tend to get a little smarter across time, especially on standardized scores. We see this. We actually have an effect for this in testing that we use in the context of psychology. Likewise, extremely bright people tend to regress closer towards the mean across testing situations. But regression towards the mean just has to do with the fact that extreme scores will pull back, because that is the very nature of regression and of associations, of bivariate associations. All right, let's talk about strength of associations and R squared. Hopefully you have all heard of R squared. If not, you have almost certainly heard of eta squared, which is quite similar to R squared. When we calculate correlations in class this week, you will see that we're calculating these based on variances. or I mean standard deviations. But standard deviations are not additive. So we can't understand how much of and they're also excuse me, also not linear. Though variance is, and variance is additive. You can reach a threshold of variance, all of the variance in your variable. So this makes working in variances more translatable than working in standard deviations. Our goal in regression is to partition y into variance that's associated with x and variance that is not. We're going to do kind of a cool exercise in class about this, but the basic regression equation is just a linear transformation of x. Since y hat, our predicted value, is the perfectly predicted value of y given x. If everything fell on y hat, remember that very first image that I showed you, then we would have a perfect linear line, or I mean a perfect linear relationship. This means that the correlation between y minus y hat, that is the correlation between the predicted value of y and x, should be equal to an absolute value of 1. And we'll test this in class. This also means that the correlation between y hat, or the residual variance, and y hat, the predicted value of y minus y hat, the predicted value of y, should be 0 because we're removing all of that residual variance from y. All right. The bivariate association between x and y is calculated using the standard deviation of x and the standard deviation of y. The way that you do this is, well, we'll do it in class. It doesn't make any sense for me to talk through it right now, but the correlation coefficient is a measure of actual overlapping standard deviations. Again, remember, I just said a moment ago that standard deviations are not additive, but variances are. So in order to understand an additive value of the magnitude of overlap, we square the correlation coefficient. And so that correlation coefficient is really the overlap in standard deviations, and consequently, the squared value is the overlap in variance. Remember that variance is just the standard deviation squared. This produces an r squared, or the amount of variance that's shared between the two, instead of shared standard deviations and standard units. This is why we use r squared. This is the whole purpose behind r squared, because a correlation is the overlap in standard deviation units, not the overlap in variance accounted for. And if you think about it, in a regression equation, what we're talking about is for every increase in x, that slope b is a increase that we expect to see in y. And so if we're looking at standard units, we're saying an increase, let's say we have a correlation of 0.6, then what we're saying is an increase of 1 by one variable an increase of 1 standard deviation by one variable should result in an increase of 0.6 standard deviations in the other variable. That's what a correlation coefficient is really telling you, and that's what a correlation of 0.6 means. Okay, statistical inference with regression coefficients. What do we mean by inference? So inference is, remember, we have two basic types of statistics. We have descriptive statistics and we have inferential statistics. And descriptive statistics are just telling us something about our data. Inferential statistics are telling us ways in which data are related. And so inference is all about understanding the ways in which two or more variables are related. We have some basic assumptions that underlie inference in regression analysis, or in all statistics, but specifically in linear regression models. The first is that we're able to distinguish between what is the dependent variable and what is the independent variable. This is a question of science and method, not a question of statistics. The values are fixed, and by fixed we mean that there is a single value for each person's dv and iv and not multiple potential values. The values of y are randomly sampled. The values of x do not necessarily need to be randomly sampled, but the values of y must be. This is why it's incredibly important that we try to gain random samples from our population. Unfortunately, most of the data that we have access to are convenience samples. This is why convenience samples are listed so frequently as a limitation, because basically they violate this underlying assumption of our inferential analysis. The residuals from the mean value of y, i.e. the error, is normally distributed. Despite what you might have heard, we always hear that we're worried about the distribution of x or the distribution of y in some cases, and whether or not our variables are normally distributed. That's less of a concern. In fact, the regression analysis is or can be quite robust to violations of basic descriptive normality, but we need to make sure that our underlying residuals do not violate basic normal distributions. And this plays to our next point, and that is that there is equal variance across the range of x. If there is not equal variance across the range of x, we have what is called heteroskedasticity. Ideally, we want homoskedasticity. We want our skedasticity to be equal. And so if you look here, we have two plots of residuals, and you can see that across time or across this regression model, at various values of x, the spread, the variability around the fitted line is not different. It's no different here than it is here. We have a normal distribution of residuals. Here, not the case, right? Things get spread out here, and they are packed in tight here. This is heteroskedasticity. Eventually, we will talk about how you correct for issues of heteroskedasticity, or how you test whether or not the issues with heteroskedasticity are affecting your analysis. For today, we're not going to worry about that. That is coming up, I think, in 2 classes. All right. Null hypothesis significance testing. This is the basic mechanism that we use to test all of our parameters within a regression model. By all of our parameters, what I mean is every one of our slopes as well as our intercept. We use this by testing against what we would consider to be the null hypothesis. Now, your book makes a point to talk about the difference between a null and a nil hypothesis. And in truth, nil hypothesis is more appropriate. Null hypothesis assumes that you are testing against a true zero. We're not really doing that, though. We're testing against a non-effect. Right? We're testing, and I suppose in a way you can say that you're testing against a zero effect, but there is never a true zero effect. There's almost always some sort of relationship. It may not be a robust relationship, but a relationship nonetheless. And so this is especially true with regard to the slope. With the intercept, it becomes a bit more complicated because it is testing against, well, not necessarily a zero, but anyway, given any given test of your null hypothesis is based on relationships amongst 4 parameters, and the parameters are listed there for you. I'm not going to read through them, but I am going to say this. These parameters are structured such that if 3 of these are true in sufficient magnitude, then the 4th necessarily must be true. And so you can read through those, you can have a look at those. They have to do with the probability of rejecting the null in the context of sample magnitude and the alpha that you have. Oh, I will make a point. Number 2, it says as alpha increases, power increases. Note that alpha is your p-value cutoff. So we think of p-value cutoffs typically as being 0.05. Another common p-value cutoff is 0.01. As we move from 0.01 up to 0.05, we increase in power, right? And so that's what I meant by the region of rejection of the null hypothesis there. All right, let's talk about the factors affecting the size of R. We have a number of factors that affect how strong or how high R is. The distributions of X and Y certainly are going to affect the size of R, and they will affect the size of R because the distributions of X and Y, if they vary greatly, can result in wild or different heteroskedasticity in your residuals, and consequently affect the overall confidence in our ability to calculate an appropriate R. We also have the reliability of the variables under study. This is why reliability becomes an important issue in every single method section that you'll ever write from here on out. Restriction of range affects the size of R. For example, one of the interesting things that we've noted as using the GRE as a predictor of success in grad school, it's that GRE scores do not predict how well a person will do in grad school or how well a person will do after grad school. And this is mostly a problem of range restriction. We only admit people in the upper echelon of GRE scores, and so we have no way of testing whether or not that predicts performance in graduate school. If we were to admit people with very low GREs all the way up to very high GREs, we could examine the correlation between that and find out whether or not GRE is a good predictor or not. Just as a side note, there is some who would argue that there is some predictive value to GRE, but also that the predictive value of GRE does not outweigh the biases that we see within the GRE itself. We'll save that talk for something in class or another time. Another thing that affects the relationship between or the size of R are part, partial, and whole correlations. We're going to talk a little bit about this in this week's class, much more about it in next week's class when we start talking about multiple regression. These are instances in which we have a number of predictors and there is variance within those predictors that account for variance in each other rather than in Y. One of the other pieces of this are things like change scores. Change scores tend to be affected by because a change score is when you subtract some value out of another value. And in fact, we'll do a kind of a fun, interesting thing in class where we look at change scores versus including a non-change score or a time one score as a predictor of time two with something else. So, then we have ratio of index scores. This becomes problematic, especially when your ratio of your index score. Ratio of index scores are when you have multiple scores that have been computed either as a ratio of something. So for example, if you have 50 people in a data set and you calculate some sort of event occurrence and divide by 50 to get the ratio of people, then you wind up inherently tying your outcome variable to the number of people that are in that data set. In addition, what we see oftentimes with ratio of index scores is when people will look at a multi-item inventory. For example, they'll add up items 1 through 10 and they'll get a total, and then they'll look at the correlation between that total and item 1. Item 1 is a portion of that total, and so it can be problematic. There are ways to handle that and ways, because this can be an important research question, you know, how much of the variance in the total is accounted for by people's response to number 1. We'll talk a little bit about that, but the ratio of that value can certainly affect the size of R. And then curvilinear relationships. As I showed you in the first couple of slides, we can have a curvilinear relationship where the relationship actually looks like it's R, but it's because we don't really understand the relationship. And a lot of times the way that we start to understand some of these things is simply by plotting them out and having a look at them. There are also ways which we'll learn in a few weeks to test for curvilinear relationships. Okay, guys, that is it for this week. I will see you all tomorrow in class. I hope you're ready to start digging into some data. And have a good week.